Carlos Plain, a professor at Durham School, explains that throughout his career, he has dedicated himself to creating a clear and detailed theory about the universe, one that he now observes and continues to refine. He welcomes the testing of his hypothesis, understanding that science thrives through such scrutiny. The James Webb Space Telescope is reshaping and questioning many of the long-standing principles in cosmology, offering an entirely fresh perspective on the universe as we move into the new year. Its ultra-deep field image has revealed considerable flaws in our prior comprehension of the cosmos. Originally designed to uncover the universe's first stars, the telescope is now challenging outdated concepts and might pave the way for a radically new direction in cosmological research. Despite these revelations, not all scientists are wary of the changes. Many experts embrace these new findings, acknowledging that it has become clear that there were significant problems with older models. For years, doubts about the universe's expansion rate, as calculated, should have raised red flags, but many in the scientific community clung to established beliefs. The cosmic microwave background, CMB, which is the oldest light in the universe, dates back to around 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to form stable hydrogen atoms. This period, known as reionization, allowed the universe to become transparent to light. In 1964, American physicists Arno Penzias and Robert Wilson made a groundbreaking discovery when they detected the CMB using advanced radio antenna technology. This discovery was long regarded as one of the strongest pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and cementing their place in astronomical history. The CMB provided scientists with a rare glimpse into the early universe, revealing temperature variations that offered insights into the conditions following the Big Bang. The CMB also became crucial for testing the universe's expansion rate and validating other cosmological assumptions. As early as the 1920s, astronomer Edwin Hubble demonstrated that galaxies far away from us were receding, with their speed directly related to their distance. This observation led to what is now known as Hubble's law or the Hubble constant. Although Hubble lacked the sophisticated observational tools that exist today, his discovery, along with the later identification of the CMB, led to revised estimates of the universe's expansion rate, which turned out to be slower than Hubble had initially predicted. Later, astronomers used type Ia supernovae, known as standard candles because of their consistent brightness, to gauge cosmic distances. These recalculated expansion rates, based on the CMB, suggested a rate of about 67 kilometers per second per megaparsec, while supernova measurements indicated a higher rate, around 74 kilometers per second per megaparsec. This discrepancy has been a point of contention in the scientific community for decades, with many scientists recognizing that there must be a fundamental issue with how the CMB and the universe's expansion rate have been interpreted. This inconsistency, referred to as the Hubble strain or the SAA anomaly, suggests that our basic understanding of the universe may be flawed. These discrepancies, which have been known since the 1990s, have led to increasing suspicion that there may be errors in the methods used to measure the CMB or perhaps even in the assumptions about the expansion of the universe over time. The gap between observed and expected expansion rates has become more obvious, and the Hubble strain now suggests that our models may require a complete overhaul. With the arrival of the James Webb Space Telescope, researchers are now receiving incredibly detailed data that could help resolve these issues in our understanding of the universe's expansion. The new information is so profound that it could dramatically alter our previous cosmological theories. The telescope is revealing galaxies and systems so ancient and developed that they imply the universe's evolution might have started long before the Big Bang, challenging old ideas. This has forced scientists to reconsider the nature of the Big Bang and how the universe itself expanded. The issue now goes beyond simple miscalculations. It's about rethinking the very nature of the cosmos. Data from the James Webb Space Telescope is unveiling a universe far more surprising than anything previously conceived. The Hubble strain, which once puzzled those committed to traditional views, is now at the heart of the scientific inquiry, challenging the assumption that our understanding of the universe may need to be radically redefined. As scientists continue to analyze these extraordinary discoveries, they are also grappling with a bigger question. Do we truly comprehend the universe? To answer this, it's essential to understand the scientific process. Cosmologists rely on complex mathematical models, careful data analysis, and logical reasoning to make predictions and test hypotheses. Their conclusions are shaped by a combination of empirical evidence, established principles, and theoretical calculations. However, science is a constantly evolving field, and theories are always open to revision as new data emerges. The term hypothesis itself implies that scientific knowledge is a work in progress, not an ultimate truth. One of the most vital data sources for cosmologists comes from the light captured by telescopes, as well as radiation and sound waves detected by radio telescopes. More recently, neutrino detectors and gravitational wave observatories have further contributed to our understanding of the universe. The James Webb Space Telescope provides an invaluable resource for studying the universe's earliest galaxies, analyzing their structure, mass, and star populations. It can also track the formation and evolution of galaxies over time. However, Webb does have some limitations, such as difficulty distinguishing between distant galaxies and massive black holes, which emit similar brightness. This realization forces scientists to acknowledge that, for much of history, certain assumptions were accepted as facts without fully considering other plausible explanations. The recent discoveries from the James Webb Space Telescope highlight the importance of remaining open to new ideas and theories. The data provided by Webb offers a critical chance to replace outdated models with fresh perspectives, much like how science has traditionally advanced through revolutionary discoveries. As scientists continue to explore the mysteries of the universe, they face the challenge of developing new explanations for their findings. These revelations are causing significant shifts in the foundational concepts of space research, leading to a reassessment of our understanding of cosmic expansion and the forces that govern the universe. Our current models of physics and astronomy remain heavily rooted in the 17th-century laws of Isaac Newton. While Newton's laws of motion and gravity have been crucial for understanding the mechanics of physics on Earth, they were eventually found to need adjustments when applied to space. This realization led to Albert Einstein's revolutionary theories in the early 20th century, especially his special theory of relativity in 1905, which transformed our understanding of space, time, and motion. Einstein's general theory of relativity, published in 1915, expanded this groundbreaking work, introducing a mathematical model to explain how massive objects cause distortions in the curvature of spacetime. While Einstein's theories were essential in reshaping our view of the universe, he himself acknowledged their limitations, believing they would never fully explain all the complexities of the cosmos. He longed for a unified theory that would connect all of physics, yet no scientist has succeeded in creating a comprehensive model of the universe. The question remains, what might this theory look like, and could it win the Nobel Prize? Among the primary suspects in the current cosmological crisis are dark matter and dark energy. These two concepts, which make up roughly 95% of the universe, remain largely theoretical because neither has been directly observed. While these mysterious components are central to our current cosmological models, their exact nature is still a subject of debate. Some researchers speculate that dark matter and dark energy may not exist in the ways we assume, calling for alternative explanations to account for the observed expansion of the universe and the behavior of galaxies. Others propose that these entities might have evolved over time, altering their properties in ways we do not yet understand. Another possible explanation involves gravity, the force that causes attraction between masses. Despite being described by Einstein's theories of relativity, gravity remains an area of intense research. Scientists are exploring the possibility that gravity may have characteristics that are not yet fully understood, or that an unknown force could be responsible for the gravitational interactions we observe. As the field of cosmology continues to progress, researchers are revisiting the constants that have long been assumed to govern the universe. Cosmology, after all, is an ever-evolving field, driven by humanity's relentless pursuit of knowledge. From the early skywatching by ancient civilizations to the modern tools we use today, every step in our journey to understand the universe has led to new mysteries and discoveries that challenge our previous ideas. The James Webb Space Telescope represents a significant leap forward in space science, offering unparalleled capabilities to explore the universe's origins and the development of galaxies. With its launch, Webb provides a new era in observational astronomy, enabling us to study radiation from the early universe with unmatched precision. Its findings could dramatically reshape our understanding of cosmic origins and evolution. As scientists continue to study these breakthroughs, they are confronted with a fundamental question. What is our true understanding of the universe? With the data from Webb, we now have the opportunity to update outdated models and expand our knowledge in ways once thought impossible. The mysteries of the universe, ranging from the Big Bang to the unknowns of dark matter and energy, are becoming clearer with each new discovery. The future of cosmology is poised for groundbreaking revelations that will undoubtedly challenge even our most established theories. Just as the universe itself is ever expanding, so too is science, driven by the endless quest for knowledge and the thrill of discovery. The James Webb Space Telescope, leading this ongoing exploration, is guiding us toward new frontiers, bringing us closer to answering the ultimate questions about existence. How did the universe begin? What is its fate? And are we alone in this vast cosmos? These timeless questions of human curiosity are gradually moving closer to being answered with every new observation. As we move forward, the James Webb Space Telescope stands as a monumental achievement in the quest for understanding the cosmos. It is more than just an advanced piece of technology. It is a beacon of humanity's relentless pursuit to uncover the mysteries of the universe. Webb offers astronomers and scientists unprecedented capabilities, providing detailed images and data that challenge established models and offer fresh perspectives on how the universe began and evolved. The impact of these findings is not confined to theoretical physics or astronomy alone. As we deepen our understanding of the universe, we are also indirectly grappling with existential questions about our place in the cosmos. The revelations brought by the Webb telescope have the potential to reshape our worldview, forcing us to reevaluate our assumptions about time, space, and the nature of the universe itself. The telescope's ability to peer back in time, uncovering the formation of the first galaxies, stars, and even black holes, might alter the timeline we have long held about the origins of our universe. Through this exploration, we are presented with a unique opportunity to broaden our understanding of not just the cosmos, but also the laws of physics that govern it. The notion of an expanding universe, long ingrained in our scientific narratives, is being subjected to new, more complex data, challenging our traditional theories. And as this new information comes to light, scientists must wrestle with the question of whether our current theories are complete or if they are merely stepping stones toward a more unified understanding of the universe. At the same time, this brings to the forefront the realization that many of our cosmological models are still rooted in assumptions made decades ago. The possibility that these models may need to be fundamentally overhauled is not just an academic question. It has profound implications for how we approach science itself. If established theories are called into question, then the process of scientific inquiry may also need to adapt, with new methods and approaches emerging in response to the data that the Webb telescope provides. With every new discovery, we are reminded of how science progresses, by questioning, testing, and revising our beliefs about the world. This iterative process, while slow and sometimes uncomfortable, is essential for advancing knowledge. The James Webb Space Telescope is a symbol of this very process, as it challenges scientists to think beyond the established paradigms and push the boundaries of what is known.